In today's video, we're going to continue talking about the fundamental theorem of algebra and looking a little bit more at both algebraically how we can find zeros for polynomial functions, as well as starting to connect it back to our graphs. And so in our first set of examples, we're given a set of polynomials, and we need to go ahead and solve for those zeros. And the way that we did this when we were solving out with quadratics is we always set the expression equal to 0 and then solve that for our x, either by factoring or brute force solving out for x, completing the square, or quadratic formula. And technically, in all of the functions that we're looking at today, we could absolutely solve these out by factoring. But don't forget, if you get stuck on your factoring piece, you could always rely on quadratic formula and still get a correct solution using that. But good opportunity for us to practice our factoring as well. So first set of examples, number 1, we have f of x equals x squared plus 9. And so if I set that equal to 0, then we need to try to isolate the x or factor out. Now, this is not factorable, but we could absolutely isolate our x. So if we subtract our 9 from both sides, well, now we have our x squared by itself, and to undo the squared, we would want to take the square root. Except when we take the square root, remember how many answers should we get? And we should have our positive or negative. But then we also have a square root of -9. So again, those are our two pieces that we need to think about. Square root of -1 is going to yield an I, but square root of 9 would be a 3. And again, I typically write the coefficient in front of the variable. And so that would come out as positive or negative 3i. Now let's compare that back to our equation. Our highest exponent was 2, so we have a degree of 2. And so we should have 2 solutions. And that's in fact what we got out when we have that plus minus. That accounts for our 2 solutions, a positive 3i and a negative 3i. Okay, number 2, similar fashion. Now I can't isolate my x as it is, but I can definitely start out by setting the expression equal to 0. And so really we're now looking at just x cubed plus 25x equals 0. But our alternate method for this is, well, we could graph it, but again, we're focusing on our algebra. So algebraically, another method that we could use would be, let's try factoring this out. Both of our terms have a common factor of x. So I can factor out that and be left with x times x squared plus 25. And if we go back to the zero product property, we know that each factor, we should be able to set it equal to 0 and solve. So let's do that. So first factor is just an x, and there's our first solution, x equals 0. Okay, second factor was x squared plus 25 equals 0. So set that equal to 0, solve for x. And again, I need to get the x squared by itself. And I'm in the same boat as number 1. I have to take the square root of a negative number. And again, 2 answers with a square root, a positive and a negative. But because it's the square root of a negative 25, well, square root of 25 is 5, and square root of that negative or implied -1 would be I. And there are our 3 solutions. And we should probably be a little bit more formal, so let's write out our full solutions for both these problems. So x solution set is a positive 3i and a negative 3i. For number 2, again, highest degree was 3. So we should have 3 solutions. And we got them. So our 3 solutions are 0, 5i, and -5i. Alrighty, problem number 3. So again, what's our degree and how many solutions should we expect on this? Well, highest degree is 3. So we should have 3 solutions. Same type of scenario as number 2. So it wouldn't be a bad idea, go ahead, pause the video, see what you get out for x, and then come back and check your work. Okay, so again, I would set this equal to 0, and I have that common x, so factoring an x out of both terms, then set each each factor equal to 0. So one solution is just x equals 0. Next solution will come out of x squared plus 100 equals 0. Moving over your 100. And we have to take the square root of a negative again. So plus or minus square root of negative 100. But square root of 100 is 10. Square root of negative 1 is I. And so our three solutions will be 0, positive 10i, and negative 10i. Okay, number 4 is a little different. We have a degree of 4 on this one. So we're expecting 4 solutions. And again, 2 different ways I could do this. I could factor this one out if I want, and I'm actually going to do that in a future problem. But right now, actually, no, that's probably going to be the best way to do this. If I get the x to the 4 by itself, we haven't done those problems yet. We're going to be attacking those next unit. So for now, let's go ahead, set it equal, and we can actually factor this. So if you think back to your factoring patterns, minus 81, well, 81 is a perfect square. Is x to the 4 a perfect square? And so I could actually factor this out as x squared minus 9 and x squared plus 9 from our difference of squares pattern. And so we have it factored. Now let's set each factor equal to 0. So x squared minus 9 equals 0, and x squared plus 9 equals 0. Well, the x squared minus 9, he actually factors out even further to an x plus 3 and an x minus 3. And so setting each one of those factors equal, and that is, mental math that we can do pretty quickly, that's going to yield a negative 3 from that first factor and a positive 3 from the second factor. Our x squared minus 9 is going to look like our previous problems. If we isolate that x squared, because again, we can't factor this one, there's no sum of squares pattern, but we can take the square root of both sides. And square root of negative 9, we already did that. That's going to be plus or minus 3i. And so this still yielded 4 solutions. So we had our positive 3 and our negative 3. Don't have quite enough room here. We have our positive 3i and our negative 3i. So I had to go on 2 lines. But there are 4 solutions. Alrighty, next problem. And again, as always, if you need to pause the video to write things down, or you want to try the examples out on your own and then restart the video to check, never a bad idea. Okay, here we go. Example 5 looks very similar to example 4. 16 is a perfect square. I'm still expecting 4 solutions on this one. And I'm going to just show you another way that you could attack this. So again, first factoring would be x minus 4, x squared minus 4, and x squared plus 4. And I could, if I wanted to, actually factor it out further at this stage. And so this is where it's a little different from the last problem. I'm still using the same mathematics. I'm still factoring out as far as I can go. And then I can set each factor equal to 0. So we would have an x plus 2 equals 0, an x minus 2 equals 0, and an x squared plus 4 equals 0. Again, each one of them yields a separate solution. So we'd have an x equals a negative 2 from the first factor, x equals 2 from the second factor, and we have to go through and solve out for the x in the x squared expression. But again, that's going to give us our 2 complex answers that we're looking for. Square root of 4 is 2, square root of that negative 1 implied is I. And so our 4 solutions end up being positive 2, negative 2, positive 2i, and negative 2i. Alrighty, number 6. So what do you think? And I can't isolate the x by itself, so next best option, let's try factoring. And again, essentially setting it equal to 0. And before I start this, how many solutions would you expect in this problem? Highest exponent is 4, so we should end up with 4 solutions. Actually, let me scooch my window over a little to give myself a little more work room. Alrighty, so factoring this out, I notice that both I can take an x squared out of. Okay, so that leaves me with an x squared plus 36 equals 0. And I can't really factor either one of those out any further, so let's go ahead and set each factor equal to 0, zero product property. Our first one, x squared equals 0, well, when I take the square root of that, I'm still going to get a 0, although technically I'm getting a positive and a negative. And I'm going to write that down just for thought process. Although technically positive 0 and negative 0 are those different numbers. But it still accounts for the 2 answers that we should be getting out of that factor. And so technically we have 0, which is a double root. So if you think back to when we were looking at graphs, and we're going to look at a few today as well, that's where we might hit x equals 0 and bounce back. Okay, x squared plus 36. And again, it's another one of these. We can isolate the x, so subtract the 36 from both sides. And when we take the square root, we're going to get that complex answer again. So plus or minus 6i. 6 from the 36, I from the negative. And so again, 4 solutions. Even though 0 technically shows up twice, you can list it just one time. We have a positive 6i and a negative 6i. But just important to note that that 0 is indeed a double root, and that accounts for the 4th answer that we were expecting. Alrighty, 2 more problems. And so these look a little different. We have trinomials on these problems. We can still factor these though. So I know most of the factoring that we had, we ended up with an x squared of some sort in that first term. And this is really not that much different from that. So if you think about x to the 4, well, it's still just x squared times x squared. So that's how I'm going to start breaking this one down. So I know I can multiply an x squared times an x squared to make that x to the 4 in the front. And so I can still use my trinomial patterns. 32, well, I need 2 factors that will multiply to make a positive 32, but I'm going to add or subtract to get that negative 12. So that means I know I need a positive and a negative. Or do I? And to get that positive, what signs do we need? You know, negative and negative. And so the 2 values that I can multiply both negative to make 32 would be a negative 4 and a negative 8. That'll get me my positive 32. And then I'm noticing, wait a second, x squared minus 4. Well, I can factor that even further if I want at this stage. So that's an x plus 2 and an x minus 2. And then we still have our x squared minus 8. So now none of our factors can go any further. So we have an x plus 2 equals 0. We have an x minus 2 equals 0. And we have an x squared minus 8 equals 0. Okay, first 2, pretty straightforward. Subtract our 2, so x equals negative 2. Second, add our 2, so x equals positive 2. And then third one, isolate your x by adding an 8 to both sides. And take your square root. So square root of 8, again, positive, negative. But technically, we really should simplify this out. So if you think about that 8, you know, any perfect squares that we can factor out, oh, how about a 4? 4 has a perfect square, so square root of 4 is 2. And so then all I need to do is write my simplified version. Square root of 4 is 2, but then we had that extra factor of 2 that was left over. And so our 4 solutions on this, we actually had 4 real solutions. We had a positive 2, excuse me, a negative 2, a positive 2 root 2, and a negative 2 root 2. Awesome. Again, go ahead, pause the video, try out number 8, and then come back and see how you did. Okay, just like number 7, we have our leading term of x to the 4, which I can divide up as an x squared and an x squared. We have 56, And let's see, we're trying to keep everything positive, all positive signs on our factoring. So we could use a +7 and a +8. And again, unfortunately, neither one of those factors any further. So let's set each one equal to 0 and solve out. And x² + 8 = 0. And in both of these, we have to subtract from both sides. So we have an x² equals a -7. When we take the square root, again, positive, negative to account for our two solutions. We have an I from taking the square root of a negative, but 7 doesn't simplify any further. So we could say ±I√7. Okay, for our second factor, subtract an 8 from both sides. And we actually just practiced simplifying that out. The only difference is, though, when we subtract that 8, we are going to have to take the square root of a negative. And so we have ±square root of -8. We know the 8 simplifies down to that 2√2. But when we take the square root of the negative, that's when our I comes out. And so x is really equal to ±2I√2. And there's our 4 solutions again that we would expect with having that highest degree of 4. So 4 solutions, we have an I√7, a -I√7, we have a 2I√2, and we have a -2I√2. All right, and those are pretty much the most complicated piece that we're actually going to ask you whenever we ask for, solving for your roots. Now, why did we go through this algebraically? Well, one of the things that you started looking at last lesson is, well, if we have these complex answers, when we graph these out, unfortunately, they're just not going to show up on the graph. So let's kind of bring this back together again with our graph problems for our last piece. So examples 9 through 12, we are going to figure out what are the numbers of the zeros, and then we're going to verify it on the calculator. So looking at our equation in number 9, I would expect there to be 3 zeros. We have a highest degree, highest exponent of 3. So I would expect 3 zeros. So then we need to go over and graph this. So let me pop over to my Desmos calculator. And I've gone ahead actually and pre-graphed these. So if you need to pause and open a separate window to graph these out, go for it. But our first function, x³ + x² - 16x + 20, again, we would expect to have 3 zeros on this, which we do. So we have one going through the -5, and then we have a bounce happening right at our point 2, 0. And so I'm going to go back to the other file. Let's sketch that out. Okay, so it goes through a -5. And again, I'm just doing a very, very basic sketch just for the overall idea of how many and what type of zeros we have. And because we had one that went straight through, that's a single root. And then we had a bounce, that's our double root. There's our 3 zeros. So technically, all 3 zeros are real. And those are our only 2 options. We could have real answers, or we could have complex answers. And that's exactly what we found when we were solving out with equations. We had some combination of real and complex answers that always added up to the total number of degree or total number of expected answers. But here's the kicker. How many of each type might we have? Let's see. Well, let's pause on that question for a second and see what other kind of graphs we have. So number 10, we have x to the 4th. And so what would we expect with our number of zeros? Okay. So we would expect 4 zeros on this one, because again, highest degree is 4. So let's look at the graph. Okay. Oops. So this is the second graph we have in there. So x to the 4 plus 12x³. Let's see, double checking that I typed everything in correctly. Awesome. And so neat feature of Desmos is you can actually click these little buttons on the left-hand side and it'll turn your graph on or off. So if you have a number of things that you want to have access to, you can always kind of pre-program those if you want. Similar kind of thing happening here. We have 1 0 hitting at the -5, 1 hitting at the -3, and 1 hitting at 1. but we do have that double root happening at that -5, 0. And again, you'll notice our ends kind of go off on the graph. If I was to kind of zoom out, I'd be able to see overall picture, but it makes it a little harder to see what's going on with those zeros. So having that zoomed in, and again, I'm just using pinch and zoom because I'm on a touch screen computer, but if you're on a laptop, you could do the pinch and zoom with your mouse pad, or if you've got a mouse wheel, that would work as well. You'll also notice over on the side, you have these plus and minus keys, so you could always use that to zoom in or zoom out if needed. Okay, so let's go back over and sketch it out. Okay, back up to our problem. And so we had a bounce, then it went straight through, and then back up again. So again, we had a double, a single, and another single. So we have 4 real zeros on this one. Alrighty, so number 11 and number 12, again, we would expect highest degree equals our number of zeros. So we would expect to have 3 zeros. So let's see what happens when we graph it. Okay. So this is the second function I have, or third function I have on here, x cubed minus 2x squared plus 9x minus 18. Only seen 1 0, one spot where it goes through. So let me zoom out a little bit. And it looks like that's the only place it goes through. So I have 1 0 that I can see. In other words, I have 1 real zero. That means my other 2, those must be my complex zeros that just aren't showing up on the graph. So we have 1 real and 2 complex. And so again, it just went through one spot on our graph, single root. And let's go back to those examples from the first page. So I had 2 complex answers. If I go back up to some of my problems that have those complex numbers, look at how many we have for each one. So in number 8, I had 4 complex zeros, and they were kind of paired up. One was positive, one was negative. So if you think back to quadratics, we called those conjugates, where we're just changing our sign. So did that happen with all of them? So let's see here. Yep, number 5, my 2 complex answers were positive 2i, negative 2i. Number 6, I had positive 6i, negative 6i. Same thing with 3 and 4, they occurred in pairs. So anytime you're looking at a graph, keep in mind you are always going to have a pair or an even number of complex roots. So looking at x to the 5th, again, we expect 5 zeros. So if we have any complex, what's the maximum number of complex zeros we could have? Yeah, we could have 2 or we could have 4, but they have to occur in pairs. Let's see what happens on the graph. Okay, so this is the last one I have in here, x to the 5th minus x to the 4th plus 16x cubed minus 16x squared. And we've got kind of this little dip happening in the middle. We have a double root happening right at 0, 0, and we have a single root happening at the 1, but that only accounts for 3 of our zeros. Let's go ahead, zoom out, make sure it doesn't intersect anywhere else. Nope, it's just going straight up and down pretty much, aside from that little dip in the middle. So let's pop back over, sketch it out, and state out our zeros. Alrighty, so it hit at 0, bounced, and then popped back up. We have a double and we have a single. So that means we have 3 real zeros, which means our leftovers have to be complex and they have to occur in pairs, and they do indeed. We have 2 complex. Alrighty, last piece, examples 13 and 14, we're going to look at a graph and try to tie all this together with how we could express these equations out. So here we go. examples 13 and 14. So in 13, it looks like I have 3 possible zeros hitting at really nice places. So if I have 3 zeros and I don't know about any other complex, would that be enough to explain the shape of the graph? Well, 3 zeros means we're looking at an odd degree, and those always occur when we have our ends going in opposite directions, and we definitely have that. So I know I have an odd degree, potentially 3. But if my ends are going up to the left and down to the right, then actually we're going to have a negative coefficient on this one. And so, possible function that we could have might be, let's see, we have a root at -1, so that would be an x plus 1. We have a root at 0, so that would just be a plain x. And then we have a root at +1, which would come up as an x minus 1. And so if you graph that out, see how that matches up with what we had on our graph. Okay, 14, again, if the ends are in opposite directions, should it be even or odd? Okay, so degree is going to be an odd function. And so definitely 2 on number 13. Again, it could be 3, could be 5, could be 7, but I can only see 3 possible zeros. We have one going through the -2, single root because it goes straight through, and we have one going through at the 0, which is a double root because he bounces. And so possible equation might be, we have our single root at x plus 2 to yield the -2, and then we have an x squared, or x minus 0 squared. And again, try graphing that out and see how closely that approximates the graph. So that finishes out fundamental theorem of algebra and kind of pulls all of our ideas together for polynomials. Definitely check out your practice, but if you need to, again, pop back into Zoom to ask any questions you need to before you start out. Or if you try your first attempt on your lesson check and doesn't go well, again, pop back in or send me a message so we can figure out what questions you have and how to get you back on the right track. If I don't talk to you, have a great day.